Okay, so thank you very much for the nice introduction and giving me the opportunity to present what we are doing in terms of brighter use of resources, which in this case is about the use of CO2. And once we start into this topic, we start up with what's called the direct use of CO2, and I will give you a couple of examples what we have achieved so far. It is about the direct use of CO2, and once we get into the topic, it is about how are we able to manage to get CO2 as a building block into a polymer solidly built in. That means use CO2 as a useful resource for the production, let's say, of a mattress or the intermediate for a mattress. And while this mattress looks maybe funny to you, you're sitting most probably on a polyurethane upholstery or a seat. And this is exactly the material where the CO2 usage is intended for. So you're kind of next to the use of CO2 potentially in the future, while you have CO2 integrated into this material while lying or sitting on this very material. So the idea, use CO2 as an abundant climate gas, use it for something useful, use it as a resource. And this is exactly what we're doing chemically, what we have developed in the last couple of years. We take propylene oxide, a high energy molecule, CO2, let it react with what's called a starter, and come up to a chemical that's called cardion, which is essentially an intermediate for the production of polyurethanes. And polyurethanes feature the CO2 that is being solidly built in a kind of a carbonate group. And this intermediate is reacted in a second step with an isocyanate to yield what's called a polyurethane, e.g. for foam applications, but many more applications, and I'll give you some examples on that. So how do we do it? It looks like always very simple, and there's lots of high tech and high chem behind it. We take the magic catalyst that enables us to let CO2 and propylene oxide react together with a starter under highly refined reaction conditions in a continuous way, as depicted here on this slide in a continuous reactor mode, to yield the CO2 polyol that is needed for the production of polyurethanes. And what looks very simple is just high-tech chemistry and high-tech catalysis, and we make the low energy propylene oxide, the low energy CO2 react with propylene oxide, a high energy molecule, to finally yield the respective polyol. And what you see here is a technical plant that has been subsidized by the German Ministry of Research and Education. And once we get further to it, this small scale plant has been transferred a couple of years technology-wise into this big reactor, multi-cubic meters that will produce this material on industrial scale, pilot scale, with a high-tech plant of 5,000 metric tons per year, in order to furnish the industry with the respective intermediate for polyurethanes. So this is existing in Dormagen next to Cologne. And as you can see, it is kind of a high-tech plant to use this technology. So what happens later on, so we kind of take the CO2 polyol, we kind of mix it with the isocyanate as shown in the middle. And what we get finally is a polyurethane foam, which looks a bit tiny, which in fact is large by 2 by 1 meters in size. If you have this continuous production site for small scale mattresses, it's a pilot plant. And if you come to the industry, you have like plants that are kind of hundreds of meters long, and you get into halls where these upholstery and foams are produced, which are just enormous. So it's just completely full with foam and materials like that. And it's the material for mattresses and upholstery. So what's the benefit? So currently we use 100% of fossil-based materials like propylene oxide to get the respective polyol made. Using this new technology, we can kind of take out roughly a 20% for the polyol of the fossil-based material, and by that reduce the carbon footprint of the intermediate in the respective manner. So there is more sustainability in it, as the carbon footprint is just being reduced, and it's just mainly because the high energy molecule propylene oxide has been taken out and replaced by CO2, which its purification is low in carbon footprint. So overall positive sustainability, as has been figured out with Professor Bardo from the Aachen University. Savings of fossil resources, lower CO2 emissions, and a positive impact on a series of other environmental parameters. So this is the basic technology behind it. That took us a couple of years, roughly a decade, to get it developed from scratch to that stage. And this is kind of a platform technology that is on offer. So I mentioned sleeping on CO2. We have some examples of sporting grounds, hockey grounds, where the glue and the overall surface is partly made of a material based on CO2. We are about to produce insulation boards, or are in pilot scale to get there. There are some further examples just with CO2 where I would like to get a bit more into detail, and washing with CO2, as these materials were looking very different, are chemically very similar. So this is a platform technology, and this has been also been acknowledged by the German President's Award. We have been one of the nominees last year. So if we get further into fibers, which is very interesting, as this is a material like for everyday purposes, and there are lots of fibers around, it needs some what's called elastic fibers. And we have developed a material, a thermoplastic urethane material that can be, well, transferred into a fiber using what's called this melt spinning process, which yields to a better sustainability and most probably also to higher productivity. So it will also contribute to sustainable development goals and make things more economic and more sustainable. That's been done with the Fiber Institute of the Aachen University, and I'll get you further into it. So there is, even if it sounds simple, there's lots of technology behind producing fiber. So you have the way how this is made within the spinnerel, and all the setups that are needed to come up with a material that is really sound for industrial application. So this has been made so far, funded by the European Union, and it is in small pilot plant and about to be upscaled. And what happens, so you take a CO2-based TPU, you have done the melt spinning process, you end up with what's called multi-filaments. These would be covered and would be knitted and transferred into textiles. We have one example with the German company Falke, and they ended up with producing high quality socks. It's a mixture of these new elastic fibers and cotton, just to make sure that they have good long-term properties and high sustainability overall. This is up and coming, and this is kind of an industrial made sock in the picture above. Let's switch the topic from propylene oxide to ethylene oxide. So chemistry-wise, this looks similar and is very different in terms of chemistry that is behind it. I will give you a few examples of what we are doing currently in that field. And we came up a couple of years ago with the Dream Resource project that showed us that making use of CO2 and ethylene oxide is working in principle. So we had up to 16% CO2 content within the respective intermediate that we do. And we started broad material testing. And we targeted molded foam, again, a polyurethane foam application, rigid foam for insulation board surfactants, again, TPU and some additives, with a series of industrial and university partners and funded by the German Ministry of Research and Education. And what we currently have is a continuous process that takes advantage of this new technology with up to 25% of CO2 incorporated. And we believe that this will contribute to the overall raw material efficiency of the materials we produce. How does it look like? We started up with the lab development, had some upscaling steps in between in a technical plant in Leverkusen. And here we do have an example of insulation boards produced by our industrial partner Pureen. It is in pilot status, so it needs further testing and trials, but shows that this technology is worthwhile doing in principle. And well, this is, as far as we know, the first kind of insulation boards based rigid foam based materials that are so far existing. And we thank all partners involved for the valuable contributions. And this is going on in development for the future. What we could also do is just simply make kind of a technology transfer from rigid foam-like materials to detergents, which essentially are surfactants based on a fatty alcohol as a starter and EOCO2 as a hydrophilic group. So it looks like as if this was feasible, if this was working, with usable processability, and might be interesting in terms of sustainability, even more benign, as it shows faster degradability of this new material in the environment. Just a few examples. Not go into too much into details. For those interested in details, I'll happy to answer question. It shows simply that kind of with the kit tool that we have at hand, we can kind of build up detergents, surfactants like materials that are very similar to the existing ones, which are fatty acids and ethylene oxide. We can adjust hydrophobicity. We can adjust what's called critical micelle concentrations. We can work on interfacial tensions and HLB values, and we can kind of mimic the existing materials while hopefully yielding a better sustainability and degradability. And again, without going too much into detail, it just shows it washes, it works like a detergent. It has about the same foam properties, and the way of doing it and the same of working as a detergent is about the same as depicted on the right picture. So what's called oil solubility is about on par with the existing ones. Again, funded by the German Ministry for Research and Education. So far onto the topic of ethylene oxide CO2 technology. We do this in an even larger scope to also exploit what's called a mixed ethylene CO2 carbon monoxide stream, where we collaborate in the Carbon for Poor project and take advantage of, again, a flue gas stream that both has CO2 for the applications mentioned and carbon monoxide, where we have access to other intermediates that can be used for polyurethane chemistry as well. An ongoing European Union funded project with ArcelorMittal and a couple of industrial partners involved. And again, thanks to the European Union for being generous in terms of funding. So once we had the so-called direct use of CO2 as it is, and let it react with an energy-rich molecule like ethylene oxide or propylene oxide, you could also form what's called an intermediate made from CO2 and use that intermediate made from CO2 to further yield intermediates that can be used, for example, for polyurethane applications. That's what we call indirect use of CO2, and I'll get you into some examples. So what changes over the last year is that we come up with lots of renewable energy, and we have to adapt renewable carbon resources onto that. So we will have renewable carbon in the future, we will have renewable power, and this altogether leads to chemicals that kind of consist of renewable fuels and chemicals. And one example would be simply to take CO2 as a starting material, reduce it to methanol using sustainably made hydrogen that further is being oxidized to formaldehyde. And this polymerizes to paraformaldehyde, what's called polyformaldehyde, PFA. And that is a very nice starting block for the formation of polymers. So hence the indirect use of CO2 for the production of intermediates and polymers. And why are we doing this? So we always end up at this very building block, paraformaldehyde, that is accessible as of today from natural gas, but could be accessible from CO2 and renewable hydrogen, and also from biomass. And if we do the comparison of these paraformaldehyde as a building block for polymers and compare it to both propylene oxide and ethylene oxide, it is lower in carbon footprint and it is renewable. And this is why we try to take advantage of that. What happens? We take this indirect use made as intermediate, attach propylene oxide onto it, and we end up with kind of a polyol that contains the polyoxymethylene moieties, and finally let it react with an isocyanate and end up with polyoxymethylene polyurethane type material. Again, funded by the German ministry, what's called Copernicus Project, and we are grateful for the support. This is a new class of material called PME polyols, polyoxymethylene ether polyols. And this has been, again, taken from scratch, like simple lab trials onto the proper polyol synthesis into material testing that's being done, again, with the Aachen University in terms of industrial research. Where are we now today? We can produce polyurethanes, adhesives, and films that exploit this new intermediate for 1K, 2K systems in terms of adhesives. We're working on a series of additional materials, and I guess we will always also be able to exploit additional properties of these materials soon. So address a wide range of possible applications. Again, coming from lab scale, transferring it into a small pilot plant. What we're about to do is to get this into a continuous process, as this is the only one that would be industrially feasible, and come up with as many industrial polyurethane applications as we could possibly make. So far, so good. So why are we all doing this? So the intention is to go into a most sustainable future as being depicted or described by the United Nations Sustainable Development Goals. And our research does have to comply with these development goals and all the other items that are written down on this slide to make the chemistry we do as sustainable as we possibly can, being as sustainable also in terms of renewable carbon sources that we exploit. So we will certainly support these sustainable development goals, and we found lots of partners who joined us in that very journey, and we are very in-depth to all collaboration partners that we have, like industrial partners. We had the Recticel company of Belgium, Puren of Germany. We have lots of university institutes in Aachen. We have a joint research collaboration with the Aachen University, the so-called CAT Center. We collaborate with lots of universities like TU Berlin, University of Ghent in Belgium. We receive lots of funding, e.g. from the BMBF, German Ministry for Research and Education, the European Union, from the Déchet, which is a German science technology think tank. Yeah, and this all is kind of research and development and catalysis between academia and industry, so bundling of all forces of ideas that has dramatically led to the acceleration of the overall research, has given us a climate for innovation, lots of support by politics, and yeah, to continue on this, we need kind of stable frame conditions. But as we said, we are continuously delivering those new materials from research stage to application, to the upscaling, and finally to the industrial application. That's about it. A short journey from the indirect use to the direct, from the direct use to the indirect use of CO2, of what we can do for the framework that is needed. And thank you very much to all who collaborated explicitly. And thank you very much to you for your kind attention.